So today we're going to be talking about the universal law of gravitation, which means we need to start by talking about gravitational force. I'm going to give you an equation for this law in a few slides, but we need to know what gravitational force is before we can really talk about universal law of gravitation. So gravitational force, we've already talked about it a little bit, so some of this is going to sound familiar, but it is one of your four fundamental forces, and that was kind of a little afterthought bullet point in your force slides in those notes about what those four fundamental forces are. This is one of them. It is a force of gravitational attraction that exists when an object or system interacts with another object's gravitational field. Okay, the force is always attractive. So if you have any two objects or systems that have mass, there will be a gravitational field created, and those fields will interact with one another, creating this force of attraction between those objects or the system and the object. And here's an example. There is a gravitational force between the Earth and the Moon. Which experiences a greater force? What do y'all think? Which one experiences a greater force, the Earth or the Moon?
It's the same force.
I'm glad. Most of you did not fall for it. It is the same. It is a force pair. Okay, Newton's third law, don't fall for that. Okay, equal and opposite forces. So the Earth will attract the Moon with a force that is equal and opposite to the force that the Moon attracts the Earth with. Okay, equal and opposite, force pair. All right, two objects like the Earth and the Moon will experience a force of gravitational attraction at a distance. They're not touching. Hopefully, the Moon is not touching the Earth. That'd be really bad news for us. Okay, and so that force is acting at a distance. It's a field force. Okay, and so despite the fact they're not touching, there's still that gravitational field that is going to pull each toward one another as those fields overlap. Okay, an object will interact with the gravitational field surrounding the other object. The gravitational force that is experienced is going to be dependent upon the masses of the object and the distances between them. And we're going to look at an equation in a minute that actually has that stuff in it. You're going to see what those relationships are between that force of attraction and those masses, and between that force of attraction and that distance of separation. Again, by the way, if you want to open these up on your own screen, you can, although right now, apparently, I did not put them in Schoology yet. They're only in My Open Math. But you do have access to this until I post it in Schoology. Just go to My Open Math to open it, in case I go too fast. All right, so we can calculate this gravitational force. And to do so, we're going to use the universal law of gravitation, which quantifies this force of attraction. It gives us a number that we can solve for. And that universal law of gravitation states that the gravitational force that exists between two objects is directly proportional to the product of their masses. And we're going to call those M1 and M2, since we're dealing with two objects, mass 1, mass 2. And inversely proportional to the square of the distance between them. Okay, and so I'm writing it out here in words, but you're about to see this written algebraically in an equation in a minute, and you should be able to see those relationships in that formula, although you are welcome to copy down those relationships here as well. You're going to see it again because we're going to go over some examples momentarily. Okay, so again, it's a way for us to calculate and get a number value for that gravitational force. And you're going to see in that equation that I give you that that force is going to be directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Here's that equation. Okay, so right here are my forces of attraction. Just like we talked about a minute ago, they're equal and opposite, right? So the force of the Earth on the Moon is equal to the force of the Moon on the Earth. We could call those F1 and F2. Either way, they're the same. So F1 equals F2. Both of them are a force of gravitational attraction, and they are both equal to this equation. Big G is my universal gravitational constant, which has a value of 6.67 times 10 to the negative 11th. That's at the bottom of my screen. The units that we use for big G are Newton meters squared per kilogram squared, and those units are just going to cancel stuff out to leave us with what we need depending on what we're solving. It does mean, however, that when you plug in numbers for these masses and for this distance of separation, that your masses will need to be in kilograms so that they cancel here, and that the distance of separation will need to be in meters so that it cancels here. Okay, so it does kind of give you an idea of what your units need to be whenever you're substituting in, and if you don't already have meters for distance, you'll need to convert it. If you don't already have kilograms for mass, you'll need to convert it. You'll probably have kilograms, but you might not have meters, because when we start talking about the Earth and the Moon, we're probably not going to measure with meters. We're probably going to measure with kilometers. So you will need to make sure to do a conversion if I give you meters. In this formula, again, M1 will be my source mass. M2 will be the object's mass that's being attracted to that source. So you might see a question that says, what is the force of attraction that the Moon experiences from the Earth? In which case the Earth would be my source and the Moon would be my object. Okay, it doesn't mathematically matter which one's which, because you're just multiplying them and the order doesn't really matter. But in some instances, you might need to be able to differentiate between the two if you're deriving an equation. The distance between them is represented by the letter R, and it's the distance between the centers of mass. So you can see how I've labeled it up there. It's not from the edge to the edge, it's from the center to the center. And we use R because a lot of times when we talk about this and we're talking about celestial objects like the Earth and the Sun, the distance from the Sun to the Earth is the radius of its orbital path. If you can picture that in your head, or you can even draw it on your paper. So that's where the R comes from, because that distance of separation is actually a radius of that orbital circular path. Okay, so again, those are the variables that show up in the equation. So when we use it, you'll be substituting in the values accordingly. You can rewrite it like this. Again, those forces are both forces of gravitational attraction, F sub g. F sub g equals big G times M1 times M2 over R squared. This is how I prefer to write the equation. And I think that's how it shows up on your formula chart as well. By the way, the universal gravitational constant is listed on the front of your formula chart up here with your constants. Okay, so you can find it on here. Yep, it is listed like this, the way I have it up here, except it says, it doesn't say FG. All right. So let's talk about some proportional reasoning. Let's look at the relationships that exist. I've already described them, so we hopefully already know what these are, but let's go ahead and take a look. It says, if I double the mass of M2, how would the force of gravity be affected? So if I double this mass, what happens to FG? It doubles, right? It is going to be directly proportional. Doubling M2 will give me twice the answer here if everything else remains equal. What if you double M1 instead? Doesn't really matter, does it? Because it doesn't matter which one is doubled. If I double either of these, it's going to result in this being doubled. And that is because this equation shows that mass is directly proportional to your force of gravity, which again, you probably already had written down if you copied down that little paragraph earlier. Okay, so again, you're going to have a directly proportional relationship between your mass and your force of gravity. So doubling one of them will double Fg. Doubling both of them would quadruple Fg. And changing it by whatever factor, it's going to change Fg by the same factor. All right, what about the relationship between distance and force of gravity? What if you double the distance so the objects are farther apart? What does that do to my force of gravity? Half's a good guess, but it's not right. Anybody know why it wouldn't be half?
It's going to be 1/4.
Why would it be 1/4?
Because it has an inverse square relationship.
Because it's R squared. Okay, so if you double that, you are dividing by that now, but it's not divided by 2, it's divided by 2 squared. If you triple it, it's not divided by 3, it's divided by 3 squared. Okay, so again, make sure you're paying attention, but radius, or that distance of separation, and that force of gravitational attraction have an inverse squared relationship. You're welcome to write that out in words, but you need to be able to apply it to a scenario like this one. If I say, if I have 1/3 the distance, what happens? You should be able to answer a question like that. Okay, so again, it is an inverse squared relationship. Just as a reminder, because we sometimes have to graph these things, especially when we have labs. If you have an inverse squared relationship, in Unit 1, we had to linearize that twice, okay? Because you had that linear or that inverse relationship, and you then had to apply the linearization for that squared relationship. So if you have something like that, you may have to go through 2 steps in linearization to prove it. In fact, we did this exact relationship in Unit 1 because I just gave you the data in a table. Okay, so again, that is an inverse squared relationship. All right, so let's take a look at something with some numbers. This one is still a proportional reasoning example, but we've got some numbers here. It says 2 stars exert 4 times 10 to the 26 newtons on each other. If one of the stars is doubled in mass while the other moves away so their distance of separation is doubled, what is the new force of gravity? So here's my initial scenario. I have my 2 masses. I don't know what they are because it doesn't tell me, but I called them big M and little m. Okay, I have my distance of separation r, and this question is describing a scenario where one of my masses is doubled. Now I have 2m over here, and my distance is doubled. Now I have 2r over here. And so we're looking at what's the new force of gravity. And I don't have numbers to plug into this equation because I don't know either mass or anything like that, but I do know the relationships. And so I can use proportional reasoning to answer a question like this. Okay, I know that my force of gravity is proportional to the product of my masses and inversely proportional to the square of the distance between them. That's what this says right here. That force is directly proportional to this. It's not equal to it because I took the g out. That's a constant. So that doesn't play any role in that. But it's proportional to that. Okay, and so I can take that proportionality statement and I can apply the changes that are described in the question. 2 times the mass. So let's put a 2 up here. And 2 times that distance of separation. Let's put a 2 down here. What does that do? Okay, well now I would have 2 over 2 squared, which I could reduce to 1/2. And so I would have 1/2 the original force that I started with. And I know what that force is. I started with a force of 4 times 10 to the 26th. So half of that would be what I have now, because the changes I just applied give me half the amount of force. Half of that, of course, would be 2 times 10 to the 26th newtons. Does anybody have a question about this example? All right, so that one's just proportions. So let's do another one with actual numbers that we can do a calculation. Yes, sir?
If you know the relationships between like the variables, and if everything else is staying constant, could you just do the relationships between the...
Yeah, I mean, that's what we did. I just showed you how I got it.
Okay.
Yes. You don't have to write that all out if you don't need to. Okay, so let's take a look at this one. If I were you, I would copy it down so that you have it to refer back to, because this calculation looks somewhat similar to some of those calculations you're going to see in your worksheet practice in My Open Math. It says the sun, earth, and moon are aligned in a straight line. The sun is 1.48 times 10 to the 9th meters away from the earth, and we're just going to pretend that that's not 100 times too close. Let's just go with it. So we are 1.48 times 10 to the 9th meters away from the earth, and the moon is 3.84 times 10 to the 8th meters away from the earth. What is the net force acting on the earth? Okay, so I've given you a picture here so you can visualize this scenario. My earth is in between my sun and my moon, and it's arranged like this. I know that the earth is therefore going to experience a force of gravitational attraction between the earth and the sun, and a force of gravitational attraction between the earth and the moon. Because both of them have large masses, both of them are going to be exerting forces on the earth, and so the earth's going to be pulled in either which direction. So I'm going to show those forces. I'm going to show the force of the sun on the earth, moving in this case to the left, pulling it to the left, and the force of the moon on the earth, which would be pulling to the right based on the way I drew my picture. Okay, so I've got 2 different forces that I need to consider, and when you have multiple celestial bodies like this, or multiple objects with mass, you're going to have a situation where you have multiple objects all pulling on each other. And so I could even find the force of attraction between the sun and the moon. I just don't need it for this question. Okay, but they would all be exerting forces on each other. All right, so net force on the earth is going to be these 2 different forces. Now, why did I draw them different lengths? Anybody have a guess?
Because the moon's mass is smaller than the sun's
I'm assuming that because the moon is so much smaller than the sun, that the force of attraction between the moon and the earth is going to be a lot smaller than between the sun and the earth. But I haven't actually solved it yet. So we're going to take a look, find the numbers, and see if that's true. We're assuming it's true based on what we know. Okay, but we can reevaluate once we get some numbers here. So here's my formula for calculating the force of the sun on the earth using my equation up here, my universal law of gravitation. And guys, I would strongly encourage you to type this into the calculator just to make sure that you're not missing the question because of an issue with how you enter it, especially if you're not super comfortable with the Inspire calculators. Please try it, make sure you're getting the same thing I do. But what I did was I took my universal gravitational constant, 6.67 times 10 to the 11th, and I multiplied it by the mass of the sun, which I don't expect you to memorize, but I do expect you to Google it if it's not in the question. Same thing in your problem set that you have that worksheet practice. If it's not in the question, Google it, okay? Look it up. Okay, so 1.99 times 10 to the 30th kilograms is the mass of the sun. 5.97 times 10 to the 24th kilograms is the mass of the earth. And in the question, it tells me that the distance of separation between them is 1.48 times 10 to the 9th, and I need to square that. Okay, so again, I would strongly encourage you to type this in the calculator because you should be getting 3.618 times 10 to the 26 newtons if you have entered it correctly. Okay, so again, take this opportunity to make sure you're typing it in correctly so that you're getting the correct answer. Because if not, we need to figure out what you're doing wrong. It is really important when you type these in that you either group those numbers together with the exponent that goes with them in parentheses like I have, or you can use the E button, that calculator notation for scientific notation, and that will group it for you. It's especially important in the denominator. Because if you don't group that and you just type divided by, and again, if it's in a fraction form, I don't think it does this, but if you're just typing it out in a line and you type divided by 1.48 times 10 to the 9th squared, and you don't group it, it's going to divide by 1.48, and then it's going to multiply by the rest of that stuff. Okay, so please make sure that you have it grouped appropriately. Does anybody have a question about this first part of the calculation? All right. Let's do the second one then. So this is the force of the sun on the earth. Same thing, force of the moon on the earth, except now I have the moon's mass, 7.35 times 10 to the 22nd kilograms, and here's the earth's mass again. So this is moon, earth, and here's the distance of separation. And so if I put this in the calculator, I get this value, 1.98 times 10 to the 20th newtons. All right, so now we have both of them. Okay, we can take these numbers and we can label them in our diagram to make it a little bit easier for us to finish because we're not done with the question. The question doesn't want to know just the force of the sun on the earth or just the force of the moon on the earth. It wants to know the net force on the earth. Okay, and so I need both of those numbers. Here they are. But I need to find the net force. Again, net force is the sum of my forces, but forces are vectors. And so before I can do anything else, I need to start by defining the positive direction. Please note also that my diagram that I drew is correct because when I solved for these two numbers, this force from the sun on the earth is larger than the force from the moon on the earth. So the fact that I drew my arrows different lengths, I just checked that. I made sure that it was right. It is. Okay, I don't know if it's perfectly to scale, but this one is bigger than this one. Okay, but we need to start by finding a positive direction so that we can find our net force. So I'm going to go ahead and define anything moving toward the sun as the positive direction because I know that's the bigger one anyway, and that'll give me a positive answer. Okay, which means the way that I've drawn my picture, I have just described anything to the left as being positive. That means that when I find my net force, I have that positive 3.618 times 10 to the 26th, and I have negative 1.98 times 10 to the 20th. If I add them together, I get my net force, which just so happens to be 3.618 times 10 to the 26 newtons. And no, it is not always going to be exactly the same as this one. It just happens to be in this case. Okay, so that would be my net force. You're going to base it on the numbers you have. All right, questions about this? No? This number is quite a bit smaller than this one, and so basically we're just subtracting decimals that we don't even see here. Okay, so that's what's happening. I know it doesn't look small, but the 26th power versus the 20th power, that's several more decimals out that we don't see with the rounding here. All right, so let's talk about, we just talked about celestial bodies that are acting at a distance, but what if we're talking about you interacting with the Earth, or a building, or anything that's on the surface of a planet or moon interacting with that planetary body? Okay, so when objects are on the surface of the planet, how do you determine their distance from the planet's center of mass? How would you know how far you are from the Earth's center of mass? Okay, well, you would add together the radius of the Earth plus your radius, or your distance to your center of mass. Okay, now, as you can probably imagine, that extra meter from your height, negligible when you're talking about the Earth being so much larger than you. And so if you're talking about something on the surface of a planet, you can simply use the planet's radius. You don't need to add in the extra height from your legs to your center of mass, okay? Because it's not going to show up in your answer anyway. It'll be in those decimals that we don't see when we're looking at that answer in scientific notation. So again, we're going to use the radius of the planet. Because any object on Earth is so much smaller than the Earth itself, we're just going to use the Earth's radius. Same would be true if we're talking about the moon or any other planet. If you have a really big object and a really small one, you can just use the radius of that planet. This is obviously not to scale. Otherwise, we would have, I don't know, really interesting things happening if there was a man that tall. But it says an astronaut stands on the ground outside of NASA. If he has a mass of 80 kilograms, what is the force of gravitational attraction between him and the Earth? The Earth has a mass of 5.97 times 10 to the 24th kilograms and a radius of 6,378 kilometers. So, if I want to determine his force of gravitational attraction, I can still use the universal law of gravitation. Same equation we just used for two planets. Now we're going to apply it to a planet and an astronaut, a normal-sized astronaut, not this guy. Okay, and when we do that and we plug in, it looks like this. Now there's one thing I want to point out. When I plugged in my numbers, you'll notice this number down here, not in my question, because I put in 6,378,000. That's because my question gave me kilometers. Again, you have to use meters. So if you have a distance of separation or a radius that is in kilometers, you do need to convert it to meters. And if you need to write down the conversion, please do so. There are 1,000 meters in a kilometer. So 6,378 kilometers is 6,378,000 meters. And you do have to convert it before you put it in the equation because it gets squared. You can't just change it afterward. You're going to get a different answer. Okay, so looking at my equation, here's my gravitational constant, 6.67 times 10 to the 11th. Here's my astronaut's mass, 80. Here's the mass of the Earth divided by the distance of separation. That's the Earth's radius squared. And when you put all these numbers in, you get a force of gravitational attraction of 783.1 newtons. Okay, and we've actually done a calculation for FG before in the forces unit. If I asked you to find the FG, the force of gravitational, the gravitational force of the astronaut, how did you do it in the forces unit? Do you remember?
Normal force.
Sorry?
Normal force.
It did usually happen to be equal to normal force, but that's not how we found it. What equation did we use? Do you remember? mg. We multiplied the astronaut's mass times the gravitational field strength of Earth. Since this one's on Earth, we should be able to multiply 80 times gravity, which we rounded to 10. 80 times 10 is 800. But guess what? 80 times 9.8, 784. Okay, so we have effectively just made our lives harder by calculating it this way with this equation because we have a shorter way to do it. Okay, so if you're on Earth, you can just multiply mass times that gravitational field strength. This number is slightly off from what I would get with 9.8 because there's a lot of rounding here. The Earth's mass is not exactly 5.97 times 10 to the 24th. There's a lot of decimals that I rounded off there and we cut off. Same thing with this radius. Okay, there's a lot of decimals that we cut off there. But it's really close. We're within a Newton. Okay, less than 1 Newton away from this exact same value. So just a heads up, you can use this, but you can also use Fg equals m times g. Okay. you will get roughly the same answer, a little bit off due to rounding error. All right, so let's talk about mass a little bit more. It's in both of those equations that we were just looking at. Okay, but mass is a property of matter that is quantized based on the amount of matter in the object or system. And there are two different ways that we measure mass in science. We can measure gravitational mass and we can measure inertial mass. And let me start by saying this. There is no difference. Experimentally, measuring it in either of those two ways, you should get the exact same answer. Okay, so experimentally, they are the same. There's not a difference between them. It's just the way that we define it that is a little bit different, and the way that we apply the calculations that we do is a little, we use different formulas depending on which one we're finding, but we end up with the same answer. Okay, so let's take a look first at gravitational mass. You're going to find gravitational mass when you are taking the mass of the object or system in a stationary frame of reference. So if the object is at rest, if you're just assuming that you're at rest right now on Earth and we're looking at it in a stationary frame of reference, you could just use that same equation I just mentioned, Fg equals m times g, if you knew the force of gravitational attraction between you and the planet, and you knew the gravitational field strength of the planet, you could find your mass that way. Okay, so you could actually calculate your mass based on your weight and the gravitational field strength. Okay, or based on that force of attraction between you and the planet and that gravitational field strength. Okay, so that's one way, that's gravitational mass. The other way is inertial mass, and we find this when we're taking the mass of an object or system in an inertial frame of reference, especially if you're talking about something that's in motion. Okay, it's a measure of an object's inertia. When we talk about inertial mass, it's a measure of inertia. And we talked about inertia in our forces unit. Specifically, we talked about the law of inertia, Newton's first law, which stated that an object at rest will remain at rest and an object in motion will remain in motion at a constant velocity unless acted on by an outside unbalanced force. Okay, and so that basically states that an object will maintain its state of motion. It has a resistance to changes in its motion or a resistance to acceleration. And you can measure a resistance to acceleration. Okay, you can do that using Newton's second law. So you can also find your mass this way. If you know the force that's being applied to an object, you know the net force applied to it, and you know its acceleration, or you can measure that, you can calculate its mass that way. Okay, so you can find mass using Newton's second law, your inertial mass. You can find mass using Fg equals mg to find your gravitational mass, but experimentally you're going to get the same number. Okay, there's no difference between the two in terms of the value you get. It's just the way that you go about finding it in the situation where you are going to apply that particular method. All right, guys, for the rest of the class period today, you are working on your playlist 1 worksheet practice and your checkpoint. Playlist 1 is due next Monday. Your bump assignment, you could also choose to work on that. That's due by Friday of this week, so if you haven't looked at it yet, that might be a good thing to look at. And again, as a reminder, please hold on to all of your labs. We will do a physics binder check on the 14th, and I'm going to be looking to make sure you have all of the labs we have done. Now, right now you should have 2. I have not yet passed back your friction lab because I have to finish grading them. And then you haven't yet received your gravitational interactions lab. You'll get it tomorrow. So you will have a total of 4. Right now you should have 2 of them in there. Okay, so if you guys have questions as you are working on these items today, please let me know. If you aren't sure where your labs are, you might want to start looking for them. But again, make sure you keep an eye on these due dates. If you have any questions, let me know.